Okay, so this is problem 2 of homework 12. And here we're asked to show that h of t, which is equal to the f conjugate of t minus t0, is the best receiver that maximizes the output of the signal to noise ratio here, where f of x is a deterministic signal, and f of n of t is WSS white noise with unit spectral density. Okay, I'll say. So since we know that, we know that input x of t is comprised of the signal f of t and some white noise n of t, and it goes into this system h of t, and the output would then just be h of t convolved with both the signal and the noise. And so y of t is going to be equal to this convolved with signal and then h of t convolved with noise, which will represent as S0 of t for the signal and S0 and N0 of t for the noise. And before we start, we want to use what we have given, and since we're given that n of t is WSS white noise with unit spectral density, that means that the S of W is going to be equal to 0, and because WSS, the expected value of n of t is going to be equal to 0. So S and R can be represented as the output signal squared, the absolute value of the output signal squared, divided by the output noise absolute value squared. And so we just have to find the top and then the bottom to find what our signal to noise ratio is going to be. So our S0 of t, as we know from before, is going to be equal to f of t convolved with h of t. And in order to make this into one integral, we also know that this is equivalent to the inverse Fourier transform of big F of W. So we're going to turn this into the frequency domain. So big F, inverse big F, the inverse Fourier of the big F of frequency times h of W, and that's equal to the integral from negative infinity to infinity of f of W times h of W times e to the j omega t tau dW. And so now we want to input in the peak time, because that is what we're interested in. And so we just substitute in for wherever we see a t, which is td. And so we now have the top part of this equation, since here we just take the absolute value squared. So this will be absolute value and a squared. Okay, so now to find the bottom part. And so we know the noise is Gaussian, and therefore S of the noise, so the spectral density of the noise, is going to be equal to n of n0 divided by 2. And so knowing that, we can plug that into the future equation. So n0 of t is going to be equal to the noise input noise component convolved with the impulse function, and that's going to be equal to the integral from negative infinity to infinity of the spectral density of the noise times h of W dW. And so when we square this component, we can see that the S of the spectral density of the noise can come out, and this will equal to the absolute value squared of the integral from negative infinity to infinity of h of W dW. And we know that the spectral density is going to be equal to n0 over 2, so that can come out and equal to n0 over 2. And then the integral can come out from negative infinity to infinity times the absolute value of h of W squared dW. So now we have both of the components of the top and the bottom of the formula for the signal to noise ratio. And so we simply just put that in. So now we have to use the Schwarzschild inequality, and that equality is defined as the absolute value of negative infinity to infinity of f1 of x times f2 of x dx squared is less than or equal to negative infinity to infinity of f1 of x absolute value squared dx times negative infinity to infinity of f2 of x squared absolute value dx. And this formula is only valid if f2 is a complex conjugate of f1. And so knowing this formula, we can now put the SNR equation into this formula format. So by applying Schwartz, we now see that the absolute value of what was before the top of the signal noise ratio, h of w times f of w e to the j omega td, or peak time, dw, absolute value squared, is less than or equal to these individual components multiplied by each other. And so when we apply that into the signal noise ratio, and we make the entirety of the signal noise ratio, we notice that the negative infinity to infinity of absolute value h of omega squared d omega is in both the numerator and the denominator. So those two can actually cancel out. And so we get signal noise ratio is less than or equal to 2 divided by n0 times negative infinity to infinity of the absolute value of f omega squared d omega. And therefore, the max SNR, since this has to be less than or equal to this, is going to be when signal noise ratio is equal to 2 divided by n0 times negative infinity to infinity of absolute value of f omega squared d omega, where h omega is equal to the f conjugate of omega times e to the negative j omega tau. And this, in the time domain, simply just becomes what we were given before, which is h of t is equal to f conjugate of t0 minus t. And so we have proven that this is the best receiver that maximizes the output, and that this is also the proper filter. Okay, so for the second part, we are asked to plot the filter responses when the input is a regular pulse of duration t. So this is going to be our f of t, and this is going to be, let's say just example, f of t of negative t. And so when t0 is equal to t, we get f of big T is less than t, big T minus t, which is just simply this, but then pushed over to the left by big T. And if you notice, when you push this over by t, since this already has length t, you just get, we just basically get our original f of t. Similarly, when the t0 is equal to t over 2, it's just pushed over by t over 2, and so instead of going full t, it just ends up being pushed t over 2 from its starting point here. And lastly, with t0 is equal to 2t, we get f of 2t minus t, the 2 big T minus small t, and that's just simply pushed over length of 2t, so it goes from negative t all the way to starting from t to 2t, and so that is problem 2.